Hello, today's topic is internal forces in beams, and this is part 2, example 4. I will show you how to draw internal force diagrams in simple beams and how to do it efficiently without writing internal force functions. Some professors require writing internal force functions to draw the diagrams, so you need to ensure whether those functions are necessary for you or if you simply need to draw the diagrams and that's it. Without writing internal force functions, the diagrams can be drawn much faster. In the fourth example, we have a continuous load. In the middle of this continuous load, I applied a concentrated force of 5 kN. Here we have a concentrated force, a moment, and I provided a support, which is movable, but at this support, we also have a moment as a reaction. It's called a vertical roller. So let's calculate the reactions at the supports. Here is the reaction perpendicular to the direction of movement, which means horizontal, so it will be 0. And as a reaction at this support, there is also a moment, ma, and the reaction in the hinged support is Vd. So I'll also determine the resultant from the continuous load. Maybe I'll divide it into 2 resultants right away, because we will have to do that for the shear force diagram anyway. So one resultant will be on the left side of this 5, which is 3 times 10, so that's 30. And the other will be on the right side of this 5, which is also 30 in the middle of that section. Okay. And the sum of moments at point D equals 0. So the moment ma plus 15 times 6. Here I wrote minus 60 in the equation, so from the entire load, the resultant times 3. Minus 60 times 3, that's it. Minus 5 times 3 plus 10 equals 0. From this, I calculate the moment at the fixed end equal to 95 kN. And the sum of projections on the y-axis equals 0. From this, my reaction Vd comes out to be 50 kN. Of course, you can do a check. I won't be doing one in this example. Now let's move on to drawing the diagrams. So the shear force diagram. Here there is no shear force at the beginning of the beam, so there's no jump. So there is, in fact, no diagram at all. So we started from 0 and only go up to this point. So here, in this section, it's 0. And we have a jump of 15 according to the arrow. Next, we consider what's happening up to this point. We drop by 30 and we drop linearly because we are under a continuous load. That is, down to the value of 15 from the other side. Okay, so it's linear. Here is 15 and here is 15. I will immediately extend the intersection at this 0 point. In that case, when we changed the sign under continuous load, there will be an extreme value at this point on the moment chart. Well, now I might not fool around with calculating the intersection. Because here you can see that since there is 15 here, there is 15 here, this intersects in half. So half of 3 is 1.5. 1.5. And then, all right, we are here, a jump of 5 down, that is, to the value of 20. I will write here that there is 20. Next, linearly to 30. That is to the value of 50. Linearly to the value of 50. Here is minus. We have reaction Vd. How much is it? It is 50. So to 0 here. Because upwards is the reversal of this reaction. And in this part of the beam, there is no shear force, so here it is 0. This is what the shear force diagram looks like. And now the moment diagram. At both ends of the beam, we have some moment applied. Here a moment is applied to the beam, and here it is as a reaction at the support moment. So, from both sides, the graph will start with a moment. Here the moment graph jumps up by 10. 10. Here ma goes down. And it is equal to 95. And now we calculate the areas of the figures. So 1.5 times 15 times 1/2. That is 7.5 times 1.5. We are calculating now, so 11.25. The area of this triangle is the same. The area of this trapezoid A plus B times H divided by 2. So 70 times 3 is 210 divided by 2 is 105. And now we can draw the moment diagram. So from this 95, I would move by this area, but the area is 0, so I will not change the value here. We still have plus. Then 11.25 towards the plus. We are on the plus side, and further deepening this plus, that is downwards. And that's already a parabola, because here we have it linearly. So 95 plus 11.25 is 106.25. 106.25 is the extreme value. Next, from this 106.25, we move towards minus by 11.25. So we subtract from this positive value. Well, back to 95. This is a parabola. So here we have 95. No, and now from the 95, which is positive, we have 105 in the direction of the minus. Also a parabola. So we will land on 10 from the other side. And that is a parabola. Yes, something like that. Plus, minus, that is a parabola, so here we have 10. And then we would like to move to this area. The area is 0, correct? We connect to 10 from the other side. Here is a negative value. So we have a drawn graph. So as you can see, even though the situations here are a bit strange, here is the force concentrated in the middle of the continuous load. Well, I think I didn't provide simple situations here, but rather ones to exhaust all possibilities. This method of calculating areas of shear force graphs and drawing moment graphs based on that is great. So we can also do this with moments at characteristic points and use the area method as a check, or the other way around. We calculate using areas and we check the moment at a point. If you think the material was helpful, I encourage you to share it with your colleagues. I recommend subscribing to our YouTube channel. Then you will be up to date with new materials and new videos. I also encourage you to like our Facebook profile. In the meantime, that's all. I wish you happy learning. Best regards. Goodbye.